similar things.
Oh, yeah, if you really want to get yourself in trouble, jam their station keeping channels. Someone will hunt you down.
And then he will say, no, but you did this wrong with the XOR. We were sending it to XOR. Look at the spec, this was wrong. We fixed it. We fixed it for you. Yeah. I'm not even sure what band is under the state. It might be S-band.
There's a term that's used at least in the intelligence world when they talk about what they call RSOCs, which are remote signals operation centers. And that's basically what you're setting up. You're setting up an RSOC. You're going to put, it's where you put the processing facility away in a different place where you can aggregate lots of data in one place.
David, could you wait a second? Is the camera on already? Or?
Yes.
Do you want it to be on tape, you just said?
Yeah, we could turn it off for 5 more minutes.
That's okay, I won't say anything.
Okay.
It's a term that's used to describe these arrangements. They're called RSOCs.
Okay. Anyway, we can continue that.
Not to be confused with GSOC.
So, yeah. That's about all the topics that we're going to talk about now. The other problems we have with TDMA specifically is the voice codec. TDMA framework is something I'd like to develop because we work a lot with TDMA systems, and I don't want to have to rewrite the same thing with slight variation each time around. So I'd like something that's generic enough to support that with the least amount of work required to implement a new system. And then Dimitri will talk about the MultiRX tool and how he sees it evolving over time.
Sorry, I just think for the recording it may be better if you can speak up a bit. I think in the
Okay.
room everyone can hear you, but I'm not sure how well it will.
We'll try to speak up for the camera.
Can you hear us, Cameron?
Someone with the makeup here and making the people nice for the camera.
Mic check. So, the voice codec. The voice codec is a proprietary IMBA variant done by DVSI. So AMB is Advanced Multiband Excitation, and DVSI is a company which only does speech codec, so that they're not really keen into sharing the information since it's their own business. DVSI actually distributes or manufactures cheap USB sticks that can be used to decode some of the variants of their codec, like the DMR variant or the APCO P25 variant. But unfortunately, I contacted them, and this stick does not support the GMR1 variant or the Marsat variant of this codec. And the cheapest they can do is the Net 2000 appliance with a special firmware that you have to order specially. And yeah, 2000 is about the price cost, which is very expensive. There are essentially no public specification. Yeah, nothing worth mentioning really. So what do we already have? Because we're not starting exactly from scratch. We know that there is 4 frame types. Tone is to transmit the pure DTMF tones. It also supports other stuff like pure sinusoidal stuff and something called the NOx tones, which is another competing system with DTMF.
So, if I may interrupt, they don't transmit DTMF and signaling messages like in GSM. They actually have special codec frames that transport the tone.
Yes, yes, and they have special frames that transport the tones, and they also have something. They even have a complete a new protocol descriptor for DTMF stuff. So yeah, it's whatever. It can also transmit call progress tones and stuff like that in the codec. And when you press buttons, it definitely transmits codec frames at least. Yeah. So the tone frames is known. reverse engineered it. It's a strong word because it was pretty obvious how it works. The only thing I haven't really figured out is I know what the amplitude field is. I have no idea how it's coded because it does not make sense to me. But yeah, mostly works. The for the voice frames, the specification actually mentioned somewhere in passing the bit allocation, where you have 9 pitch bits, 6 gain bits, 6 voicing bits, and 27 spectral bits, and some more in the class 2 section. Something I should probably explain is a multiband excitation codec works by essentially taking a given spectrum between 0 and 4000 Hz or 3700 Hz. It divides it into equal sized chunks of spectrum, and for each of them it will send a voicing decision. The voicing decision says basically, this part of the spectrum is going to be created either by feeding a pure tone and filtering it, or sending noise essentially, and filtering that to a given amplitude. For all of these bands, then they have another division, which is the pitch, where what you do is you have a base frequency, which is expressed in those 9 pitch bits and the 2 LSB. There is only the 9 pitch bits that define the base frequency, and then for each harmonic it will also send an amplitude. So mostly the parameters that you need to recover is the base frequency, the voicing decisions, and for each of the band, and the spectral amplitude for all the harmonics of the 9 pitch bits. We have to stand the P25 EMB and AMB are specified in the P25 standard, so we already got that. Unfortunately, they're not exactly the same, but we kind of guess that there is some inspiration. We also have the patents. Something I didn't note is that we also have the DSP code of the SO2510, which implement the codec somewhere in there. Perhaps we have no idea where, and the codec is much more complicated than the ciphering algorithm, so it's not that easy. This is what's missing, is everything else. Actually, yesterday, Frank Stevenson asked me if there was any area where he could help for GMR. And so I told him that we're looking for the voice codec, so he's actually looking into the DSP ROM. I started reading the patents and the AMP specs to try to guess how it all fits together. One of the main problems is that the voicing decisions, there's only 6 bits allocated here. In most of the patent, they talk about either 8 or 16 bands, and they basically use a lookup table for those 6 bits lead to 16 other bits or 8 other bits. And we need to find that table somewhere because we want to just invent it, obviously. And the spectral encoding, this is basically how each harmonics is the amplitude of each. Yeah.
But wouldn't it, I mean, it sounds a bit like, since it's divided in all these different frequency bands, wouldn't it make sense to just put a frequency generator or function generator at the phone and transmit lots of different tones and then see what the codec outputs?
The code that I put in the example data is exactly that. I hooked up a function generator and sent that, and I couldn't really make any sense. Okay. I do see some tone. The thing is, most of them are being translated into tone frames because they're pure frequencies. And so the phone detects that and sends a tone frame instead. That's why the tone frame is the only resolution.
Yeah.
Maybe you send some harmonics in the meanwhile, so that we come to the tones.
It can actually send a combination of tones as well.
Okay.
Yeah, the codec is very efficient, unfortunately.
So actually, for a company that spent a lot of effort compressing speech, words, which are, it's not actually that you would have MP3 that should encode all kinds of good music. I would expect a lot of voodoo going on and having lookup tables and special cases for thousands of special cases. So
There is a lot of effort went into the reconstruction to make it sound. I mean, when you read the patents, what they spend a lot of time doing is improving the reconstruction so that it sounds more natural. But even if you don't implement all the magic that they use, for example, they literally spend pages explaining how to reconstitute the phase of the signal of each band because it's not transmitted, so you have to reconstruct it artificially. And to sound more natural, they developed several techniques to do that. But if you don't apply those techniques, you have something that is still intelligible. It's not going to be the same as the phone, it's not going to be as good, but you should be able to understand it, and I'd be good with that as a first step.
I mean, the structure of voiced human speech it's a harmonic sequence that's been run through like an equalizer. So yeah, if you can reproduce that type of harmonic sequence, something that matches human forming frequencies in a very controlled way, and shoot that through, and then watch change the pitch, and watch the pitch fields. You'll spot the pitch fields.
The pitch fields is the first one. I'm pretty sure of that because that's how it is in all the other variants, and they also use special values of the pitch value to identify the other type of frames. But the main problem I have right now is the spectral, the equalizer value, essentially, the spectral amplitude is something that they compress a lot. And because depending on the base value of the pitch, you will have a different number of harmonics falling into the range from 0 to 3,700 Hz or something.
Right.
And so decoding the 57 bits of spectral amplitude, I think, is the main problems. I'm trying to. There is a library called MBElib that decodes the APCO25 codec.
Right.
I'm trying now to understand that code, but it's not very documented or particularly modular or whatever. There is another piece of code that I became aware of, is that in the P25.OsmoGMR, there is an EMBA decoder as well. But it's written for fixed point, which means when there is some magic going on, you need to differentiate between what is the codec itself and what is the fixed point magic. So yeah. So that's essentially all for the voice codec. So yeah, I kind of didn't have time to write those, so I'm just gonna try to explain my vision of it. First off, I don't want to duplicate too much functionality with the new radio. New radio does some stuff very well, like filtering and processing continuous stream of data is something that new radio is really meant to do, and it works well for that. I don't really want to rewrite it all over again. It's sometimes a pain to compile, but once you have it, it works. So it's not as CPU efficient as I hope. Maybe I would have loved to see New Radio use my GPU to do that, because channelizing is essentially something that GPU would be good at, I think, because it's stream. You can, if you have 10 channels to process in parallel, they're completely independent. So I think it would be pretty good at that. Unfortunately, New Radio doesn't do it right now, but that's something I can live with. So, but what comes after, that is demodulation in New Radio. I mean, I never could use New Radio itself and the basic demodulation blocks for something that is not a continuous, stream. When you have something where the phase is discontinuous or which is burst by nature, the Müller and Kostas loops and stuff don't lock at all, because I mean, at the end of the burst they're still not locked, and then they have noise and they go completely.
What Tom Brandau, who is a maintainer of New Radio, what he said to me, that they are working to add more features to support packet radio systems.
Yeah.
So there is some features that are already in but not very well documented. I mean, and they will be working on that for the next release of New Radio. Yeah, so that's just a comment. From
I might have a look, but from here I started working on the.
Yeah.
That's why I know the BTS, the only piece of New Radio you can actually use was the USB interface.
Exactly, yeah. And that's good.
Yeah, but if you also.
So after the current plan is to take basically channelizer and essentially the tool that's been written by Dimitri, and take as input synchronized flow of samples that are pre-filtered and everything that New Radio does well, and then feed that to a framework where that would work essentially like the Calypso phone works. That is, you have a definition of the multi-frame that defines exactly how your different channels are timed on the TDMA, and then for each call value a piece of code that says, okay, demodulate that and feed that to the upper layer, and then you can enable more frames and things like that. The actual implementation of the Calypso right now is very limited, because it's a small embedded target. You can't start allocating memory and stuff like that. But here we're talking about running on the PC, where you can do malloc if you want to allocate some stuff dynamically, and have more flexibility, like enabling 20 tasks at once is you can't do that in the Calypso because the DSP can't do it. But here we don't have this kind of limitation. So yeah.
It wouldn't be that hard to repurpose layer 1 of OpenBTS to do this.
Yeah, possibly, yes.
All you need is, all you need to do is to add a piece of sync. I'm assuming there's something akin to a synchronization channel.
Yes, of course.
Just add something to sync, and then once you're synced, you keep a virtual frame number coming from your radio, from your AD converter. You maintain a virtual frame number. And once you're synced, you just record the offset between the virtual frame number and your actual frame number. And then once you have that offset recorded, everything just falls right out.
Yes, but it's not. Yeah, it's not only the frame number; it's a sample number, because sometimes they're not aligned. Yeah, but a lot of. I'm actually looking forward to your talk about the radio modem, because a lot of the signal processing in OsmoGMR has been the API has been heavily influenced by the SIG protocol.
And actually, you might want to talk to Thomas Zhu, because he's right now rewriting, re-implementing the GSM decoding for C64. He also basically rewriting the TDMA code for DSP.
Yes, I know that he's working on that, but it's still a little too much tied to GSM
Yeah, I mean,
I need something, but yeah, definitely it's I know that I need to look at some example, some code that exists to see a better architecture.
yeah, what I mean that it would be nice if like your TDMA code would fit into what Thomas is doing, so like we could reuse the code.
Yes, I'll have to see with.
And also he wrote the demodulation and all that stuff which you could reuse, not from Narrative but from him because it's.
Yeah, but
it's-
the modulation I really want to actually rewrite it myself to understand how it works. So because I could also just retake the code from OpenBTS or from Probe and just because I'm guessing, but I want to really understand how it works. Well, because that's mostly why I do this, is to understand how this works.
Yeah. How do we, yeah.
Dimitri, if you want to talk about the MultiRX tool.
Probably will do it from here because it's just 3 slides, so I guess it's okay.
Do you need to see the projector? It's
Just
included here.
Yeah, please just switch to the slide. Yeah, okay. So we have that capture tool as part of the GMR project. So when I already explained what it does, basically it down sample or down converts a particular channel, applies filtering and also if necessary some resampling. And it writes to a file, which also could be a FIFO to forward the data to or GMRX and FIFO. And it automatically chooses all the required resampling parameters in an intelligent way. The code is actually a contribution from Survein in Python. So we ported it to C++. And you basically have just to call it with RFCN numbers you are interested in. As well as call it a little simplified, you can also choose antennas when using G devices or some gaming values for a particular channel of your underlying hardware. And the current state is it supports the USOP, UHD, and FCD interfaces or hardwares. Okay, that's the current state. Currently, we are in the process of refactoring it because there are some very interesting other hardware projects coming up, like OsmoSDR or most recently the Archealistar from Steve. And this is starting to make the actual code be very hard to understand because you currently it decides on at compile time which device is being used. So I'm trying to introduce some sort of abstraction library which provides some common interface with functions needed for all of these nice devices we have. So currently I'm refactoring the code to put the source out of the actual application and maintain it side by side. Also, the actual channelizing tool supports a concept of channels where information is stored about target sample rate you want to have after the tool has done its processing, and also filter bandwidths basically. And the idea is to support all the protocols we are interested in, and if you want to extend it for any new protocol, you just extend the channel definition file, which is basically a class, C++ class, with 2 numbers, and you have everything working without modifying another call. And another item we're working forward to is to actually, because the new devices are becoming cheaper and cheaper, and yeah, it would be interesting to have a scalable solution. So you just enter the channel numbers, and the tool opens the required number of hardware sources and distributes the channels evenly over the available hardware devices. So you don't necessarily need a wideband, expensive wideband capturing hardware, but just use a bunch of cheap receivers, especially, for example, on Turaya L-band. We have lots of channels, at least in Germany, lots of channels centered around 155.5 megahertz, and also down at 150.35 megahertz. So they are pretty much apart even for USOP. And this way you could just use two receivers and receive also channels which are very much apart from each other. Another example is receiving uplink and downlink at the same time. Of course, the devices must be synchronized in some way, maybe a common blocking source or something like that. Another functionality we will introduce is to use another or more computationally efficient way of applying channelization using a polyphase filter. That is only possible in systems which are using a well-defined channel scheme. So, for example, Tetra wouldn't work because you have some 6.25 channel granularity or something. But all the stuff like GSM, DECT would also work for this, and we would reduce the computational effort dramatically. Okay, and last but not least, the file import, also very straightforward to implement, and this would introduce also some relative entering functionality for channels. So currently you're working with RFCNs or also directed frequency for Tetra, but you also can enter relative channel offsets, so not necessarily absolute values. So you just look at the FFT, what's inside the file, you enter the offset, and it channelizes very well. Please, next slide. Okay, and that's the more distant future. The very nice to have, like an automatic, call it war driving mode. So you can just let it run automatically, and when new channels appear, it will change the flow graph to follow the channels or automatically receive them. I think there is some sort of integration available. Oh, I'm sorry, that's something missing. Oh yeah, integration of available demodulators. Because currently we're using fixed channel bandwidths, and if our RF hardware is off the frequency, the actual channel is being cropped by the filter. And for example, the Turaya demodulator gives a lot of information about frequency offsets, so we could, by putting the capture tool and the demodulator together, we could use the actual frequency error information to make the acquisition better. Also, support for GPU offloading of channelization would be very nice. So we talked already about it. And basically, yeah, I would like more hardware testing, because currently I just have a funky dongle and USOP one device. So I will try also to test this Osmo SDR and the RTL SDR stuff. And the very last item, which I personally would have on the first, we'll see when it happens, that will also show nice, yes, you can imagine like a nice FFT view, which shows basic signal information like GSM, cell info. So you just open the window and you see quickly how the spectrum occupied, what's going on. So that's the outlook.
Okay.
Thank you. That's, I think, everything.
Yes.
Oh yeah,
That's
right.
for another
That's
time.
the next session.